Black holes have a reputation problem. Ask almost anyone what a black hole is, and you'll hear the same description: a cosmic vacuum cleaner, a space monster, an object so dangerous that it swallows everything nearby: matter, planets, even light itself. For decades, popular culture has treated black holes like the ultimate destroyers, and sometimes even like something that can erase information from the universe. But how much of that is actually true? Because here's the twist: under the right circumstances, black holes don't just end things. They can also shape galaxies, regulate star birth, and, surprisingly, help create new stars. To understand why, we need to slow down and unpack what a black hole really is, what it isn't, and what we think happens at its edge. A black hole isn't literally a hole you could point to in space like a tunnel or a pit. It's a region where gravity has become so intense that space-time itself is curved inward in a way nothing can climb back out from once it crosses a certain boundary. That boundary is the famous event horizon, not the solid surface, not a physical wall, but a point of no return in the geometry of a space-time. And black, that part is less poetic than it sounds. Black holes don't shine the way stars do, and if you're looking for light coming from inside the horizon, you won't find any. Because the light can't escape. What we see instead is their impact: stars orbiting something invisible, gas heating up and glowing as it spirals inward, and jets of energy blasting away from the region around them. If you ask a physicist, an astronomer, and a mathematician what a black hole is, you'd get different angles on the same truth. Astronomers focus on what black holes do to nearby stars and gas. Physicists focus on how gravity behaves when it becomes extreme. Mathematicians focus on what Einstein's equations allow space-time to become. And all of them run into the same uncomfortable fact: inside a black hole, the rules we rely on don't behave normally. So how does a black hole form in the first place? The most widely accepted pathway is gravitational collapse. When a very massive star runs out of fuel, it can no longer support itself against its own gravity. The core collapses, the outer layers may explode outward as a supernova, and what remains can become an object so compact that space-time is forced into that no-escape configuration. Not every star can do this. If a star isn't massive enough, its collapse stops earlier, leaving behind a neutron star or a white dwarf. Only the heaviest cores, after shedding mass through winds, eruptions, or the supernova itself, can collapse into a black hole. The exact thresholds depend on details like composition, rotation, and how the star evolves. But the basic idea is simple. Mass alone isn't enough. It's mass compressed into a small enough region that matters. And that small enough has a name: the Schwarzschild radius. This is the critical radius where if you squeezed an object inside it, it would become a black hole. The surprising part is that the radius is often tiny compared to the object's original size. If the sun could somehow be compressed down to roughly a few kilometers in radius, it would become a black hole. Earth's Schwarzschild radius would be about the size of a marble. In other words, almost anything could become a black hole in principle, if you had a way to compress it enough. In practice, nature only manages it with extreme mass and catastrophic collapse. Now here's where the story gets weird. In general relativity, the event horizon is the boundary where escape becomes impossible. Cross it, and every future path you could take, no matter how fast you accelerate, points deeper inward. From that point on, outward stops being a direction you can travel toward. But the event horizon is not like hitting a wall. If you fell into a large black hole, you might not notice the moment you cross the horizon at all. There's no glowing line in space, no sudden jolt, no cosmic alarm. A useful way to picture it is this. Imagine walking through a pitch black room. If there were a physical doorway, you'd feel the frame, the hinge, the threshold. But the horizon is not a doorway made of matter. It's a change in the structure of space-time. In some scenarios, you could drift across it without any immediate sensory clue. What happens next depends on the black hole's size. For smaller black holes, tidal forces near the horizon can be lethal. Gravity would pull much harder on your feet than your head, stretching you into a long strand. This grim process has a nickname that sounds like a joke, but it isn't. Spaghettification. For supermassive black holes, millions or billions of times the sun's mass, the horizon can be so large that the tidal forces right at the edge might be relatively gentle. You could, in principle, cross the horizon without instantly being torn apart. You'd still be doomed, but not necessarily immediately doomed. And that leads to one of the strangest features of black holes. Different observers can tell very different stories about what happened to you. From your point of view, if you're falling freely, you cross the horizon and continue inward. You don't feel a dramatic stop or freeze. You simply fall until you approach regions where the curvature becomes enormous. From the point of view of someone far away watching you fall, things look different. As you get closer to the horizon, your signals take longer and longer to escape. Your light becomes more red-shifted, dimmer, stretched to lower energy. In their view, you appear to slow down, fading away, never quite completing the crossing in any practical sense. So, did you fall in, or did you freeze at the edge? In a way, both descriptions come from real physics. They aren't just philosophical disagreements. They reflect how time and light behave near extreme gravity. But the moment you bring quantum physics into the conversation, the confusion becomes a full-blown paradox. Because quantum mechanics insists that information can't simply disappear. If a black hole swallows an object, its atoms, its patterns, its state, does that information vanish forever behind the horizon? If it does, that seems to violate the foundational principle of quantum theory. If it doesn't, then where does it go? This dilemma is known as the black hole information paradox, and it became dramatically sharper after Stephen Hawking's most famous contribution to the field, the idea that black holes aren't perfectly black. According to Hawking's argument, quantum effects near the horizon allow black holes to emit a faint thermal glow, now called Hawking radiation. A helpful mental model involves virtual particles fluctuating into existence near the horizon. One falls in while the other escapes, carrying energy away. Over unimaginable stretches of time, that energy loss means the black hole gradually loses mass, very slowly evaporating. But there's a catch. If the radiation is purely thermal and carries no detailed imprint of what fell in, then when the black hole eventually evaporates away, the universe seems to have lost information. That's the paradox in its sharpest form. Gravity appears to delete what quantum physics demands must be preserved. Over the years, physicists have proposed multiple routes out of this trap. One influential family of ideas comes from string theory, where the fundamental stuff of reality can be described as tiny vibrating strings. In that framework, a black hole may not be an empty region with a hidden point like singularity in the classical sense. Instead, it could be a complicated, stringy quantum object, sometimes described with a metaphor of a fuzzball. In fuzzball like pictures, the black hole's microstructure isn't tucked away in a perfectly sealed interior. The information is encoded in the quantum state of the object itself, and what we call the horizon may emerge statistically rather than being a clean, featureless boundary. The key idea is this: if the black hole has real microscopic structure, then the radiation it emits doesn't have to be perfectly random. Subtle correlations could carry information back out, preserving quantum rules without requiring the universe to break its own accounting system. That kind of solution also connects to another deep issue: entropy. A black hole is an extreme entropy machine, so much so that the entropy associated with a black hole is famously proportional to the area of its horizon, not its volume. When you start tracking how entropy should behave during evaporation, how the emitted photon's entropy compares to the black hole's entropy, things can get messy if you insist on a purely classical interior. Modern approaches often involve accounting tricks that are anything but trivial, including ideas related to wormholes and the geometry of quantum spacetime to make the information ledger balance again. All of that might sound like abstract theory until you remember the original accusation. Black holes destroy everything around them. Even that is only partly true. Yes, a black hole can tear stars apart if they wander too close. Yes, it can gulp down gas and grow, and the region near it can be violently energetic. But black holes aren't cosmic Roombas drifting through space, vacuuming up galaxies. Most of the time, they behave like any other massive object. If the sun were replaced by a black hole of the same mass, Earth's orbit wouldn't suddenly spiral inward. We'd freeze in the dark, but we wouldn't be sucked in just because a black hole exists. And here's where the story flips from destruction to creation. When black holes feed, the infalling gas doesn't always go quietly. Magnetic fields and spinning disks can launch outflows and jets, streams of particles and radiation that punch into surrounding space. In huge galaxies with extremely active black holes, those jets can heat gas up so much that it prevents star formation. The gas can't cool, can't clump, can't collapse into new stars. In that sense, black holes can shut down stellar nurseries. But in some environments, especially smaller dwarf galaxies, the effect can be gentler. Instead of blasting gas apart or superheating it, an outflow can compress a cloud just enough to push it over the edge into collapse. And collapse is how stars are born. Observations with space telescopes have highlighted cases where an outflow from the vicinity of a black hole appears to be slamming into dense gas, changing its structure and triggering new star formation rather than suppressing it. In other words, the same engine that can sterilize a region in one galaxy might light the spark for star birth in another, depending on scale, power, and environment. That matters for a bigger mystery: how supermassive black holes formed so early in the universe. If small galaxies can host black holes that influence star formation, and if black holes and their galaxies grow together, then dwarf galaxies might preserve clues about the earliest stages of that growth. Studying these systems could help explain how the universe went from the first stars to the giant black holes we now see anchoring massive galaxies. So are black holes dangerous? Absolutely, up close. Are they simple cosmic villains? that only destroy? Not even close. They bend space-time so intensely that they challenge our best theories. They force general relativity and quantum mechanics into the same room and make them argue. They reshape their surroundings, sometimes suppressing star formation, sometimes triggering it. And they might even encode information in ways that we're only beginning to understand. If black holes feel like monsters, it's mostly because they live at the edge of what our physics can explain. But the more we learn, the clearer it becomes. They aren't just the universe's shredders, they're also its architects. Strange, powerful objects that can turn destruction into structure and force us to rethink what space, time, and reality really are.